In this video, we're going to cover section R6, and this is the last section of the review chapter that there is homework assigned for. So this section is on exponential and logarithmic functions. So the objectives that we are going to cover in this section are how to convert an exponential equation into an equivalent logarithmic equation, how to convert a logarithmic equation into an equivalent exponential equation, how to solve for x within an exponential or logarithmic equation, and how to evaluate a logarithm. Okay, and to do all those things, we're going to utilize properties. So hopefully you've seen problems that involve logs and exponentials before, and this is just, again, meant to be sort of a review because we're going to need to remember those things for later on. All right, so our definition of a logarithm. The logarithm of base a of y is the number x for which a to the power of x is equal to y. Equivalently, we could say that this equation, a to the x equals y, if and only if, we would write log base a of y equals x. So basically, these two things mean the same. Log base a of y equals x is what we call logarithmic form, and that's the same as, notice that this little number, the subscript, is the base of the log. That's also the base of the exponent over here. The value of the log, what the whole thing equals, is the exponent attached to that base, and that's equal to the argument inside of the log function y. So the base a must be positive and not equal to 1, okay, meaning greater than 0 and not a 1. So we're going to practice utilizing that definition both directions. So they want us to rewrite each exponential equation as an equivalent log equation. Okay, so these are all in exponential form, right? These are just facts about exponents that we already know. 2 to the 5th power is 32, 4 to the 2nd is 16, 6 to the 1st is 6, 3 to the negative 2nd can be written as 1 divided by 9, meaning this 3 would move to the denominator and make that 2 a positive, right? So 3 squared on the bottom, so why there's a 9 on the bottom, and then any number to the 0 power, or 7 to the 0, is equal to the number 1. So these are just exponential equations. So we're trying to utilize our definition of a log next to figure out what they would look like in log form. So anything that's in exponential form like this can be translated into something in logarithmic form. So using the definition of a logarithm, we get, so the exponent 5, the base is 2, and it equals 32. So in log form, we would say logarithm base 2, notice the base of the exponent and the base of the log should match, of 32 is equal to the value 5. The exponent is always what the entire logarithm equals. Also, you cannot say log base 2 and not have a number follow that. Okay, this is like the inside part of a function. So if I just say log base 2 equals, that makes no sense. It's like saying the square root and not putting a number underneath the square root sign, right? It's like the square root of what? Here we're saying log base 2 of what? So you have to have a value right here, and that's whatever the exponent expression equals. So the base of the exponent is the base of your logarithm. The value of the exponent is what the whole log equals, and then the value of the exponential expression is the argument or the inside of the log function. So I know this is, you have to get used to using it if you haven't used it in a while or are not familiar with it. All right, using the same procedure here, 4 to the 2nd equals 16 means logarithm base 4 of the 16 would equal the 2, which is the exponent. This one, log base 6, this base 6 coming from this number, of 6, which is the number over here, equals the exponent 1. Here it would be log base 3 of the 1/9 equals the negative 2. And log base 7 of the 1 equals 0. Just a matter of knowing where to put each part of the exponential expression into the equivalent corresponding location in the log expression. All right, so we're going to try again here. Here we're given exponentials. We're going to rewrite them as log. So this is where you should probably pause the video, try these on your own, write them down, then come back to the video to check your answers. So this part A, 5 to the third equals 125, means log base 5 of 125 equals 3. Part B, log base 9 of 1 over 729 equals negative 3. And part C, log base 15 of 1 would equal 0. All right, next we're going to solve for x within each log equation. So this time we're given a log equation, so we're given the log form, and we would like to solve for x, meaning we're going to have to turn this into exponential form, so going backwards. All right, so rewriting an exponential form, we see that the base is 2, right here, the base of the log is 2, and that the exponent would have to be 6, because that's what the whole thing equals. So this would translate to saying the base of 2 to the power 6 is equal to what's inside. So 2 to the 6th equals x would be the equivalent exponential form. So we just evaluate 2 to the 6th to get x, and that would be 64. Part B, same thing. We're given a log equation. We'd like to solve for x. So we translate to exponential form. Here the base is 3, means to the power of x, so the exponent would be x. So 3 to the x would equal 1/3. So that's just translating to the exponential version. Therefore, 3 to what power would give me 1 over 3? Well, that would mean the power would have to be -1, right? 3 to the negative first would make it equivalent to 1 over 3. Here you could translate this right side 1/3, knowing it's 3 to the negative first, and then since the bases match, the powers would be equal. Log base x of 49 equals 2. So here your base is x, your exponent is 2, and it's going to equal 49. So the base is x, the exponent is 2. Rewriting it, we get the base to the power 2, so x to the power 2 equals 49. So here we're solving this equation, meaning you're going to square root both sides. So that means x would have to be either -7 or +7. But remember, since bases of exponents must be positive, what we said using our initial definition, that would lead you to the conclusion that you can only have the positive value of x equals 7. Log base 16 of x equals -1/2. So this time we're going to write 16 to the -1/2 equals x, using the definition. So the base is 16, the exponent is -1/2, so 16 to the -1/2. I know it's kind of hard to see the negative because it's lining up with that fraction bar, but that should be a negative sign, equals x. So 16 to the -1/2 means 1 over 16 to the +1/2. The 1/2 power means the square root, so that's 1 over the square root of 16, or 1 over 4. All right, here are our properties. First property, log base a of the product mn equals log base a of m plus log base a of n. So the log of a product equals the sum of the two logs. Log base a of m divided by n is log base a of m subtract minus log base a of n. So the log of the quotient is the difference. Log base a of m to the power b is equivalent to b times log base a of m. So the exponent on the argument can be brought down in front as a coefficient. Log base a of a is 1. So when the base of the exponent, the base of the log and the argument are the same, the power would have to equal 1. In other words, this base to what power equals a, right? A to the first would equal a. So when they match, the value is 1. The first three require that m and n are both positive, so just keep a note of that the arguments there would have to be positive. Next property, log base a of 1 is 0, so no matter what the base is, if the argument is 1, the answer is 0, because this left side means a to what power is equal to 1. Well, the power is 0, any number to the 0 power always equals the number 1. This next one is called change of base formula, when we have to evaluate a log that we can't use our calculator directly for. Now, some graphing calculators have a built-in template where you could just evaluate any base that you want, but not all of them do, and scientific calculators usually don't. So this is a way to do that if you don't have a way of inserting a base yourself. So log base A of m you can find by taking log of any base of the m, divide that by log of any of that same base that you used on the top of the a. So the key in your calculator that just says log on it, log, that's base 10. So if you had to do log base 2 of 6, you could do log of 6 divided by log of 2. So we'll be doing some examples with change of base. Log base a of a to the k is simply k. Because if the answer has to be a to the k, it's what power of a is a to the k, well, the kth power. So when the bases match, the answer is the exponent. Remember earlier we said log base a of a is 1, meaning that if the power is not listed, right, that's assumed to be a 1. So that would also fit property 7. And for any x that's positive, if your logarithm is part of the exponent, if the base of that log matches the base of its exponent, then the answer just is simply the x. All right, so here we're given some values. Log base a of 2 is given to be 0.301, and log base a of 3 is given to be 0.477. So using those given facts, we're going to find the following. Log base a of 6. So we're given log base a of 2 and log base a of 3. So utilizing one of our properties, we should be able to find the log base a of 6. Reason is because you can write 6 as 2 times 3. Right? 6 is the same as 2 times 3, so that's the same as log base a of 2 times 3. And then we said earlier that the log of the product is equivalent to the sum of the separate logs. So that product property would change this to log base a of 2 plus log base a of 3. And then, again, they're just citing property 1. And then we're just plugging in what we know. Log base a of 2 was given and log base a of 3 was given. So we plug those in and evaluate. So 0.778. All right, this time log base a of 2/3. So we can use our quotient property to rewrite this as log base a of 2 minus log base a of 3, and then plug in the given values for the logarithms that we were given on the other slide and evaluate. So negative 0.176. All right, log base a of 81. So remember, we were given log base a of 2 and log base a of 3. So if I notice that 81 is a power of 3, we would rewrite it as 3 to the power 4. That's the same as the number 81. And then our property 3 says if you have an exponent attached, that can come down to the front. So that's 4 times log base a of 3. And we knew log base a of 3 was given to be 0.477, so we plug that in and evaluate. 1.908. All right, log base a of 1/3. We're going to start the same way and split this up into log base a of 1 minus log base a of 3. This time, we know log base a of 3 was the 0.477, but this time log base a of 1, when the argument is 1, remember it does not matter what the base is, so that's one of our properties. Property number 5, so that would just be 0. So from there we can evaluate negative 0.477. Log base a of square root of a. Again, we're going to rewrite the square root of a as the power of a half. Once we do that, notice here that the base of the log matches the base of the exponent, so the answer should just be the exponent. So we should just get 1/2. That's property 7. Next, we have log base a of 2a. So we're going to split that up into log base a of 2 plus log base a of a with our product property again. Splits to the sum. Log base A of 2 was given initially to be 0.301, and then here, log base A of A, remember that the power, like up here, the power was a half, that's what we got a half. Here the power is 1, so that value would be 1. So 1.301. All right, log base A of 3 divided by log base A of 2. Here we just were given those two things, so we just substitute in our values that we were given on that initial slide, and we get 1.58. Log base A of 5. This one we're going to kind of be stuck on because earlier when we started off, when we had our very first part here was log base A of 6, we could write 6 as 3 times 2, so we could do the problem. But 5, you can't write as anyway using 3's and 2's unless you write it as the sum. But if you just change this to log base A of 2 plus 3, there's no property that allows you to split up if the sum is on the inside. In other words, log base A of 5 is not the same as just adding them. Log base A of 2 plus log base A of 3 combined together would be log base A of 6. Because you multiply, not add. So we can't do this problem with what we were given. All right, when the base is 10, the number log base 10 of x is what we call the common log of x. So a lot of times you will see that written as just log x. So that key on your calculator that says log on it, L-O-G, when you utilize that button, it's evaluating logarithm with base 10. So if I just wanted to find log of 45 on your calculator, if you have a graphing calculator, you type log first, hit the log button, plug in 45, press enter. 1.65321. On a scientific calculator, depending on the calculator, you'll have to play around with the one you have. Sometimes you would type in 45 first and then press log. Sometimes you'll type log first and then press 45. So you just have to know how your calculator works. So I would practice that. All right, log base 5 of 12. Okay, so without a template, okay, so on a scientific calculator or one that doesn't have a template, you'd have to use change of base for this one. So you would use our change of base by utilizing your base 10 button. So you'd have log base 10 of 12, so just log of 12, divided by, again, log base 10, or just the log button of 5. So log of 12 divided by log 5. All right, if you have a TI-84, okay, if you press the math button, there's a math key kind of on the left-hand side of your keyboard, and then scroll down, you may have an option that says log base. So if you press math and scroll down and have that option of log base and press enter, it'll pull up to your keyboard a template where you can just put a 5 in the box as the base and the 12 in the box for the argument and just type that in directly without needing the change of base formula. And either way, if you type this in your template or if you use this formula, you should get 1.54396. Same thing on this one, log base 6 of 27. So log of 27 divided by the log of 6, which is 1.83944. Or if you pull up your log base template, you can put the 6 as the base and the 27 as the argument and get the same result. All right, so how about let's find log base 7 of 21 and log base 30 of 5. So change of base formula would look like this. 1.56458 or the template. Log base 30 of 5, so log of 5 divided by log of 30. Change of base or the template, 0.47320. So I would practice those, make sure you know how to do those on whatever calculator you plan to be using on a test. All right, and that is the end of section R6, and that concludes what we're going to cover out of the review chapter.